imagine if you're given two vectors A and B. Let's assume both of them are row vectors, right? Let's assume I have A1, A2, so on, so forth, AN. Similarly, vector B, which has B1, components B1, B2, so on, so forth, Bn. Now, mathematically, let's learn some very basic operations. What about addition of A and B? If I add these two vectors, what do I get? I simply get, it's basically called component-wise addition, A2 plus B2. So what I'm doing here is, I'm basically taking the first component from both A and B and I'm summing it up. That becomes the first component of A plus B. Let's assume A plus B equals to C. Similarly, I'm taking the second component here and I'm summing it up here. Right? Very, very straightforward idea. So on and so forth, AN plus BN. This is how you add two vectors. Very, very simple idea. This is the addition of vectors. Then the immediate question that comes to your mind is there something like multiplication? Because we learned all these concepts in simple algebra, right? So is there a concept of multiplication of two vectors? There are actually, for vectors, there are two types of multiplications. There is something called a dot product and a cross product. There are two types of multiplications. So some of you who have studied physics in your 11th and 12th grades would recall what a dot product is and what a cross product is. So just for simplicity, we don't use cross product much in machine learning. So I'll not go into the details of what a cross product is. But let's go and understand what a dot product is. So if I'm given two vectors A and B, a dot product is written as A dot B. Right? First, I'll explain the notation and then we'll go and understand the geometry behind it. So A dot B is nothing but, you take again, it's a component-wise multiplication. A dot B is nothing but A1 multiplied by B1 plus A2 multiplied by B2 plus A3 multiplied by B3, so on and so forth, AN multiplied by Bn. You might ask, okay, this multiplication part seems logical to us, but why are you adding? Just take it from me that this is just notation. Okay, just let's assume we are understanding notation. I promise you I'll connect it with geometry very soon, very quickly. Okay, so for now, let's define it this way. Now, if I write it in vector notation, what is this? A1, B1 plus A2, B2, A3, B3, so on and so forth. I can actually write it in vector notation, right? I can write it as A1, A2, so on and so forth. If I have a row vector for A, and if I have a column vector for B, B1, B2, so on and so forth, Bn. Some of you might have studied about multiplying matrices and multiplying vectors in your 11th or 12th grade. So what does this mean? This basically means that, so this is, first of all, let's remember, this is a 1 cross n matrix, or a 1 cross, it's basically a row vector. This is a column vector, which means it is n cross 1. As long as this and this match, you can multiply them, right? So since this is n and this is also n, you can multiply these two vectors, or these two matrices if you want to think about it. This is a matrix with only one row, this is a matrix with only one column. Right? When I multiply them, the simple matrix multiplication that we all learned in high school, it's nothing but A1 multiplied by B1 plus A2 multiplied by B2 and so on and so forth. Right? Now, from a notation standpoint, typically whenever somebody says a vector, they typically, just for notation's sake, they typically refer to it as a column vector. So whenever somebody says A is a vector of size n, what do they mean? They typically mean that A is a column vector. This is just for simplicity. Whenever somebody says a vector, by default, it's a column vector. Because there's always this confusion, is a given vector a column vector or row vector? If nothing is explicitly told about it, you have to assume that it's a column vector, sorry. Right? So what we have here is a row vector of A and a column vector of B. This is also written as, numerically, this is also, for simplicity, when you have a row vector, let's assume I have a row vector A1, let's assume I have a column vector, just for simplicity. I have A1, A2, so on and so forth, AN. Right? Let's assume this is my vector A, because the default representation is always a column vector, which is of size n cross 1. Right? N rows and one column. All right. Now, what does A transpose mean? A transpose means basically swap your rows with columns and columns with rows. So A transpose, for some of you have learned basic linear algebra in your high school or 11th and 12th grade would immediately recognize this. A transpose is nothing but A1, A2, so on and so forth, AN. So I can convert a column matrix, a column vector into a row vector by just taking an operator called transpose, and this becomes 1 cross n. So going back to our previous example, what we have here literally is nothing but A transpose multiplied by B, right? So you can write A dot B as nothing but A transpose B. And what does it all boil down to? It boils down to summation of 1 to n if A is an n-dimensional vector, AI, BI. This is what a dot product is from a pure linear algebraic perspective. But now let's go and understand geometrically what does A dot B mean, because that's important, right? We have to connect geometry with linear algebra, because if you don't connect it, we don't understand what a dot product means in higher dimensional spaces, because we're doing all of this linear algebraic exercise to understand geometry. So let's assume we live in a two-dimensional space, or we have a two-dimensional space. Let's assume I have a vector A and I have a vector B. Of course, A has two components, A1 and A2. B also has two components, B1 and B2. Right? Now, when we have these two components, this is your vector A, right? This is your vector B. Now, what does A dot B represent geometrically? A dot B can be written as, I'll explain what each of them mean. Okay, let's assume the angle between A and B is theta, and the length of A. So this is nothing but the length of A, length of vector A, and this is your origin, right? So length of A is nothing but distance of A from origin. Similarly, this is length of B. So length of a vector is represented with two dashes surrounding it. Okay, this is nothing but length of a vector. Okay, so what is A with two bars behind it? It is nothing but this length. This length. Let me just highlight it for you. It is nothing but this length, and this length is nothing but B. So A dot B is nothing but the length of A multiplied by length of B multiplied by cos of the angle between them. Right? Now this is very useful. Now if somebody gives you two vectors as A1, A2, how do you determine what is the angle between them? Right? So let's quickly see that. So if somebody gave you A and B, I can write A dot B as A1 B1 plus A2 B2, which is also equal to length of A, length of B cos theta, which means theta is nothing but cos inverse of, some people also call it arc cos inverse of A1 B1 plus A2 B2, right, divided by length of A and length of B. And we know that length of A is nothing but A1 square plus A2 square under root. We saw this, right? Distance of a point from an origin in one of the previous videos. So this is the length of a vector. So if somebody gives you two vectors A and B, you can easily find the angle between both of them if you just know the components A1, A2, B1, B2. Right? I can still write. So basically, I can write this A, the length of A, as A1 and A2. So if you just give me the components of A1, A2, B1, B2, I can find the angle between those two vectors. Now this takes us to an interesting idea. What if I have two vectors? Let's say I have two vectors. Okay, I have a vector A here and I have a vector B here. Let's assume they're perpendicular to each other, which basically means the angle between them is 90 degrees. Okay, let's assume this is x1 and this is x2. Two dimensions, right? Your A is A1, A2. Your B again is B1, B2. Now, the quick question is, if I know that A dot B, what will A dot B be like? Okay, length of A, length of B, and cos of 90. And I know that cos of 90 is 0. So A dot B will be 0 because this is 0. Right? So if a dot product between two vectors is 0, we know that those two vectors are perpendicular to each other, right? So remember, this whole idea of angle between two vectors can be extended to any dimensions. Your A could be any dimensional vector, A1, A2. It could lie in any dimensions. It could lie in an n-dimensional space. B2, sorry, B also can exist in an n-dimensional space. It doesn't matter. Even though we can't visualize anything more than 3D, your A and B could be in any dimensional space. I could just compute A dot B, which will always be length of A and length B and cos theta, right? Which means I can compute the theta as cos inverse of AI BI summation, right, by length of A and length of B. So if you give me two vectors in any dimensional space, I can compute the angle between those two vectors. I can compute the theta between A and B very, very easily, because what I've learned in 2D, I'm just extending it to n-dimensional space, right? This is what I learned in 2D, right? Whatever I learned in 2D, I'm just extending it to n-dimensional space. Similarly, if I have two vectors in n-dimensional space, and if I compute A dot B, what is A dot B? A dot B is nothing but summation over I equals to 1 to n, AI BI. If that turns out to be 0, I know whatever dimension the space that A and B could lie. All that this implies that A is perpendicular to B, right? I don't care whether you're operating in 2D, 3D or ND. This is the beauty of linear algebra. In linear algebra and coordinate geometry are very nicely connected through relationships like this. And whatever we learn in 2D, we can easily extend it to ND, because vectors could be of 2D, 3D or any dimensions. And all the geometric intuition that we're learning from 2D, we can extend it to any dimensional space. Now the next question is, what about A dot A? What if I multiply, I do a dot product of A with A? What does A dot A actually mean? It basically means A1 into A1 plus A2 into A2, so on and so forth, AN into AN, and this is nothing but A1 square plus A2 square, so on and so forth, AN square. And this is nothing but the distance of A from origin squared, right? We know that given any point A, its distance from origin is nothing but A1 square plus A2 square plus so on and so forth, AN square under root, right? We know that the distance from origin, D, can be written as this. And when we do A dot A, what we get is basically square of the distance of that vector A from origin. And this is in any dimensional space. The theory still just holds good. That's the beauty of it. So what we've done is, we have written dot product in 2D, right? We have written about dot product in 2D, right? And we've understood it geometrically as angles between points. And we're extending the same idea to n dimensions, because dot product can be generalized to n dimensions. And from that generalization, we're understanding the n-dimensional geometry without being able to visualize it. That's the super duper power of linear algebra.